So today we have a guest from Chile, Professor Francisco Tello-Ortiz. Francisco is going to tell something about the gravitational decoupling, which is an approach using in general relativity. Francisco has a big experience working on this approach, so he's going to talk about some basic introduction about the gravitational decoupling. And I think it's going to be about some special case, which we call the minimal geometric deformation. So Francisco, whenever you want, you can start, okay?
Okay, thank you, Jorge, for the presentation.
I have some problems. Listen to me. I have some problems with my.
Everybody can hear me. Can you hear me, Jorge?
Now, yes. I can hear you now.
Okay, thank you. Okay. Okay, I was telling that, first of all, thank you very much for inviting me to give you this seminar. Thank you very much to Ms. Teresa Kapushova and Pabla Bijova for the organization of this seminar. And also I want to thank to Professor Jorge Valle and Professor Zdeněk Stužlis for inviting me to stay with them during October and November at the Silesian University in Opava. Thank you very much again. So today I'm going to talk about gravitational decoupling by minimal geometric deformation. Okay, it should be just an introduction about this subject. First of all, okay, this is the outline of my talk. Okay, a small motivation behind this methodology. And then we are going to discuss the gravitational decoupling building blocks, the minimal geometric deformation approach and its meaning, how to grow the theta sector, and then some physical and astrophysical consequence in applying this theoretical methodology in studying, for example, compact star or black hole or wormholes. And then conclusions. First of all, allow me to present you gravitational decoupling evolution during this last 5 years, okay? Professor Jorge Valle and his collaborator almost since 5 years ago, they have developed this methodology, okay? And since 2017, as you can see in this graph, there has been a growing interest in working in this subject. It is a very active research field, okay, with almost 4,000 citations, okay. In this plot only I have considered, I have collected only the information concerning gravitational decoupling by minimal deformation approach, because it is worth mentioning that there is an extended version of this methodology. But as I told you before, today only I am going to talk about the minimal geometric deformation approach. This methodology has been used not only in the context of general relativity, also in the context of the brain world to explore new black hole and wormhole solution, in the context of cosmology and some modified and higher gravitational theories as FRT gravity, for example, Lav law gravity, and Gauss-Bonnet gravity. Okay, what is the main aim behind gravitational decoupling? Why this methodology was put forward by Professor Jorge Valle and his colleagues? As you know, sometimes if you are looking for some analytical solution to the Einstein field equation, this is not an easy task, okay? We know that Einstein field equation are a quite complex system of equation, non-linear partial differential equation. And even if you are, for example, assuming that the space-time geometry, for example, is the most basic one, for example, as a spherical symmetric and static space-time, and also if you are assuming a perfect fluid matter distribution or a vacuum space-time, it is not easy to solve these field equations. Then we can ask us, what happens if we couple matter source to the perfect fluid that present more complex or realistic scenarios? What is happening if we go beyond the perfect fluid scenario of if we go beyond the vacuum scenario? The answer is simple. The situation changes radically, making it almost impossible to obtain analytic results, okay? So the above situation, I mean, now we are starting from a spherical symmetric and a static space-time subject to a specific matter distribution, okay? I shall assume along the talk this situation. Obviously, if you want, you can start from a quite complex situation. For example, it is not necessary to assume a spherically symmetric space-time, or you can start from an anisotropic fluid distribution. But just I want to illustrate how this methodology works when you start from the simplest solution, okay? A spherically symmetric and a static space-time subject to a perfect fluid matter distribution. As you know, we have here the Einstein field equations, okay? We have here this part encode the geometry of a space-time, and this part encode the matter distribution. PF mean perfect fluid, okay? I'm assuming this scenario, this example. So the question was, what is happening if you include another kind of source, okay? Beyond the perfect fluid, or you are coupling the perfect fluid with another source, a new source. It means that you are modifying the energy momentum tensor, okay? Here we have the usual Einstein tensor again, but now our energy momentum tensor is not longer the perfect fluid matter distribution, because now it includes, for example, a new source, okay? Originally, this source is represented by this tensor, okay? This theta mu is another form of gravitational source, but it could be a scalar field, for example, vector field, or a tensor field. And you are coupling this new form of gravitational source through a dimensional coupling constant, this alpha. But now you need to solve this problem. Einstein field equation, okay, is equal to a quite complex form of the energy momentum tensor. Okay, this is not only is this the perfect fluid, but plus this unknown tensor or gravitational source. Then, originally, in the seminal articles here by Jorge Valle and then his collaborator, they were wondering about this one. Would it be ideal to solve Einstein field equations by solving the field equation for each gravitational source individually? Please take into account now, we have the usual Einstein tensor, but now I'm including an extra source. Then the question is, can I solve this problem for each source separately? I mean, first of all, I am going to solve for the perfect fluid, and then...
sí, simple.
Sorry? Okay. Then I am going to solve for the theta mu source. It is possible to do that? This is the question. Then we want to solve this problem. We have the full Einstein tensor, okay? This is equal to the full matter distribution now containing the perfect fluid and the theta mu tensor, okay? But we want to solve this problem, not the full problem given in equation number 4. Just we want to separate them and solve the part corresponding to the perfect fluid solution, okay? Here you have the Einstein tensor associated with this perfect fluid solution. And also you have the energy momentum tensor. And obviously this equation has associated a metric tensor, okay? Associated to the perfect fluid space-time. And also we want to solve this second problem. okay, the problem associated with the new source, with the theta mu new source. But as you can, as you know, Einstein field equation, I say that, are nonlinear partial differential equations. Then, if you are trying to solve one problem, and then the second problem, if you are trying to split this problem, in principle, it is not possible, because then the final solution, you want that the final solution should be a simple combination of the metric tensor corresponding to the perfect fluid solution and to the theta sector. But what's the problem in doing so? A superposition problem, principle, sorry, for Einstein field equations? You know that superposition principle works very well when you are working with linear differential equation, with linear equation. In this case, it should not be possible because we are facing the problem of a system of non-linear partial differential equations. Nevertheless, this methodology, the so-called gravitational decoupling by minimal geometric deformation approach, allowed us to solve this issue. So Einstein say us, okay, try it. Of course, let's see. Again, suppose this the simplest situation, okay? You start from a perfect fluid matter distribution. As you know, this is the energy momentum tensor, okay? You have density, the energy density, the isotropic pressure, and the forward velocity of the fluid. Also, we are assuming this line element, a spherically symmetric and a static line element, take into account that both metric potential, the temporal one and the radial one, only depends on the radial coordinate. And here we have the usual two sphere. If you plug this information into the field equations, into the Einstein field equation, we are obtaining this set of equations, the set of equation 9, okay? Here you have the component of the perfect fluid energy momentum tensor, and here you have the component of the theta sector. Please remember that we are including this new source, and here you have the geometric part of the Einstein field equation as usual. But in this case, if you count the degrees of freedom, you have density 1, the theta TT component 2, the isotropic pressure 3, theta RR 4, theta 5 and both metric potential. Then you have 7 unknowns. And before introduce the theta sector, you only had 4 unknowns: density, pressure, and both metric potential. In principle, as you can see, we are not gaining anything because the number of unknowns is increasing. Then if you are trying to solve this equation in analytical way, it should be quite complicated. Nevertheless, if you are introducing this new source also is in principle introducing new information. We know that Einstein tensors satisfy Bianchi identities, okay? The divergence of the Einstein tensor is equal to 0. If then it's happening, it means that the full energy momentum tensor should satisfy this condition too. When you compute this subject to the spherically symmetric line element, you find this conservation equation, equation 12. And now you can see the first consequence of introducing the theta sector in the system. Okay, the first consequence, was at the beginning, you start with 4 unknowns, functions, and now you have 7, okay? The problem is more involved. But now, at the level of the field equations, at the level of the conservation equation, as you can see, this term represents the usual hydrostatic or conservation equation associated to the perfect fluid matter distribution. These two terms are the corresponding one, okay? This represent, for example, the, okay, sorry, here is a mistake. This is not ET, this is RR. This is equivalent to the hydrostatic gradient, okay, introduced for the theta sector. And this is the gravitational gradient, but now the theta sector is introducing an anisotropic behavior into the system. Remember that I have started from a perfect fluid matter distribution. It means that lateral pressures and radial pressures are the same, okay? But now the theta sector no needs to satisfy this condition. No need to satisfy this condition. Then the equivalent to the lateral pressure and radial pressure at the level of the theta mu sector are introducing an anisotropic behavior, as you can see in this last term. So it is obvious that at this stage, if you take the limit alpha tending to 0, you recover the original problem. In this case, I started from a perfect fluid matter distribution subject to a spherically symmetric line element, okay? So, first consequence of introducing the new theta mu source. As I told you, before entering the theta sector, we only had 4 unknowns, okay? Both metric potentials and 2 energy momentum or thermodynamical variables, okay, rho and p. Now we have 7 unknowns, both metric potentials, the original density, the original pressure, and the component of the theta sector. But just 3 equations. Then it is obvious from the mathematical point of view that we cannot solve this problem, okay? We cannot solve this system to find out 7 unknowns if I have 3 equations. And also, the system becomes anisotropic in nature, okay? Because the theta sector introduced local anisotropies, and these anisotropies are encoded by the so-called anisotropy factor given by delta. Then, the question was, can I couple different kind of matter to this perfect fluid matter distribution, and then can I solve them in a separate way? In principle, as you can see, there is no way. There is no way because I have a quite complicated set of equations with 7 unknowns. But if you introduce the so-called minimal geometric deformation approach, you can solve the problem. You can solve this problem. But how it works? How it works? The first step is to consider the original problem. I mean, alpha equals 0. It means there is not an extra source. Okay, theta mu nu is not there, and we are trying to solve the GR problem. I mean, we have a spherically symmetric and a static line element subject to a perfect fluid matter distribution. Okay. This is the usual definition, and here you have the usual gravitational mass definition. But then, suppose you perform the following maps. Maps 15. I mean, you take the temporal component, okay? You take the temporal component and the radial component of the light element, and then you translate them performing this map. You are coupling now 2 unknown functions, g and f, okay? This function are function depending only on the radial coordinate, okay? This is so because in this way you are preserving the spherically symmetric symmetry of the space-time, okay? And you are coupling these 2 unknown functions the so-called deformation function or the decoupler function in the same way as you introduce the theta mu component, the theta mu tensor, okay? Using this alpha parameter. Then the third step, set one of the deformation functions to be 0. When you set one of the deformation functions to be 0, then you are on the so-called MGD approach, minimal geometric deformation approach. It means that you are minimally deforming the space-time, okay, where one of the metric components remains unchanged. In this case, as you can see here, I'm setting to be 0 G. It means that the temporal components remains unchanged, okay? Remains being the same, but I'm modifying the radial metric component. I'm modifying the metric radial component. Then, through this map, if you plug this map into the field equations, you can separate the problem in two different set of equations. One of them is the usual Einstein set of equations, as you can see here in 17. Those are the Einstein field equations subject to the conservation equation, the hydrostatic equation or TOV equation. And the second system contains the information, the full information of the theta sector and the corresponding deformation function, F. But the system of equation 18 also is satisfying a conservation equation. Okay, also is satisfying a conservation equation. Moreover, as you can see here, this system, the theta sector, has some contribution coming from nu. And what is nu? Nu is the temporal component of the space-time. Okay. Then, in some way, in some sense, okay, it is obvious that both systems are related through this function. As you can see, the problem, first glance, the problem seems to be strange. I mean, I have started from a quite complicated energy momentum tensor. Then we have introduced a deformation function, okay? And after that, after some algebra, we have obtained two separate systems of equation. One corresponding to the Einstein field equation, the usual one, and a second one corresponding to the theta sector and its associated geometry encoded into this decoupler function with its respective conservation equation. Then, what are the second consequence of introducing the theta sector? The first one is the system of equation is already solved by the so-called SIT solution. It should be clear soon, okay? The set of equation 18 contains 4 unknowns. Let us see. This set of equations, okay, contain 4 unknowns, the full component of the theta sector and the deformation function, okay? And it is supposed that this set of equations, the usual Einstein field equation, are already solved by the so-called SIT space-time. At the beginning, I told you that this methodology was proposed in order to solve Einstein field equation, okay, finding out analytical solution. Nevertheless, this problem is quite complicated. Then, what are, sorry, then here we are employing this methodology not to solve the full set of equation at all, okay? We are not solving this quite complicated system of equation with 7 unknowns at all. Just we are introducing new ingredients, okay, to represent more complex and real scenarios, okay? But assuming that we have an unknown solution, a seed space-time, okay, already satisfying the Einstein field equations. And then our task is to find out the new sector, just the new sector, because this sector, sector 17, described by this equation, is already solved. You know what is rho, what is p, mu, and nu. And obviously, these functions are satisfying the set of equation 17 and also the conservation equation. Our task is to solve the system 18, and then we need to couple this system to the seed system or the seed spacetime or seed solution to find out more complex model and realistic models. For example, here I'm talking about a perfect fluid matter distribution subject to a spherically symmetric line element. And then you can think about, for example, that this toy model could represent, for example, neutron star or quark star, for example. We know that if you drift apart from the perfect fluid scenario and if you introduce local anisotropies, you are representing or describing a more realistic situation, okay? So our task is to solve this system now. Then, but here there is a consequence when you split or separate these two systems using the minimal geometric deformation approach. The third point is, in comparing both systems, 17 and 18, the first two equations of the set 18 have a missing term -1/r² with respect to the set 17. This system is called as quasi-Einstein system field equations. Let us see. Here you have, for example, in this equation for the density, you have these three terms, okay? But this term, the same is happening in the second equation. If you compare this three equation with this three equation, you can see that this equation has a missing term. And this missing term is just -1/r². So in this case, we are solving an Einstein field equation and also a quasi-Einstein field equations. This is quite strange because it is supposed that Einstein tensor is satisfying Bianchi identities. But what about a quasi-Einstein tensor? It is satisfying or not the Bianchi identities? This is the question arising in this case. And to give an answer to this important question, to this important issue, we have the most important consequence is that both systems are conserved independently. I mean, at the beginning, we started with a Einstein tensor equal to an effective or total energy momentum tensor, the perfect fluid plus the theta mu. But it is obvious that if the Einstein tensor satisfies Bianchi identities, the effective of the total energy momentum tensor too is satisfying the Bianchi identities, okay? But in this case, how this zero comes here? How is possible to get zero here? Okay, we have two ways. First of all, covariant derivative of the perfect fluid matter distribution is equal to 0. And also the covariant derivative of the theta mu sector is equal to 0. Then it is obvious, 0 plus 0 is 0. But there is another way to get this 0 here. Suppose that the covariant derivative of this tensor is equal to minus the covariant derivative of this sector. Okay, in this case, when you are applying the minimal geometric deformation approach, we are on the first scenario, on the first situation. I mean, The covariant derivative of the perfect fluid, it is obvious 0 because it was a known solution, but also in independent way, independently, the covariant derivative of the theta mu nu sector is also 0. It means that this source only interact gravitationally. There is not an energy exchange in this case. Then, after that, you can ask me, for example, but okay, this theta mu nu sector is satisfying the conservation equation. Then how it is possible? Because in Einstein theory, in the pure Einstein theory, this equation is a linear combination of these three equations. But here you have an Einstein tensor, okay? Satisfying the covariant derivative equals 0. Consequently, the T mu nu is equal 0. But here, you have not an Einstein tensor, but your energy momentum tensor is satisfying Bianchi identities. Okay. This is a very good question, and this is the answer to this question. Okay, this is the answer to this question. First of all, the conservation equation associated to the theta sector remain being a linear combination of the field equation of the theta sector. Nevertheless, okay, nevertheless, one can formally identify, okay, the theta sector field equation as Einstein equation for an anisotropic system with energy momentum tensor given by 19. I mean, we have theta mu nu, but you can redefine your theta mu nu energy momentum tensor, theta mu nu star, okay? But by including this term, but when you compute the covariant derivative of this term has a vanishing covariant derivative, okay? Then you can rearrange your set of equation, your new sector, to satisfy Bianchi identities, and we are not violating anything. This is the most important thing. It is worth mentioning that this last term, obviously this specific form corresponds to the spherically symmetric and static line element. If you are changing the space-time geometry, obviously this term should be different, okay? But in this case, it has this form. Then if you compute the conservation equation of this energy momentum tensor, you will obtain 20. And this is the same conservation equation obtained before for the non-star T mu nu tensor, okay? And this tensor has associated this line element, this metric, okay? Then, how to close the theta sector? This is our task. We need to solve the theta sector, okay, under physical and mathematical grounds, okay? To find out new solution or to extend, for example, in this case, perfect fluid matter distribution to an anisotropic domain, for example. Then the question is how to solve the theta sector, because we have three equations, four unknowns, because these three equations are leading to the conservation equation. Then the conservation equation is a linear combination. We cannot use it, okay? And we have four unknowns and three equations. Mainly you have three alternatives, okay? The most commonly used in the literature. For example, you can impose an equation of a state. You can impose, for example, a linear barotropic or non-linear barotropic, non-local equation of a state, for example, relating the theta components. If you do that, obviously you will obtain a differential equation, okay, in the deformation function. Then you can solve it, and then you are closing the problem, because after find out the deformation function f star, then you come back to the set of equation and you finally find out all the theta mu nu components, that the problem is closed. This is one alternative. Secondly, impose some suitable physically motivated restriction or form on the decoupler function, okay? All the time we need to keep, okay, the physical content of our solution, okay? And the third one is relate one of the theta sector components with one of the seed energy momentum tensor components. That is the mimic constraint approach. Okay, I have decided to put this as a third alternative to close the theta sector because in this case, it was the seminal form, okay, or the seminal proposal by Professor Jorge Valle to close the theta sector. But I have decided to put this on a third option because in this case, you are trying, as the constraints say, mimic, you are trying to restrict the theta sector, one of the components of the theta sector, to have the same behavior as one of the components, for example, of the original or of the seed energy momentum tensor. Okay. And here in this talk, I'm going to talk about the mimic constraint approach, okay? Because here you can impose, as you feel, any equation of a state or any form of the deformation function. But the mimic constraint approach encode an interesting, I can say, encode an interesting situation. The most commonly used are this mimic constraint. First of all, the radial component of the theta sector is mimicking the behavior of the radial pressure, okay, of the isotropic pressure in the radial direction. If you equate both field equations, you can solve an algebraic equation to find out the deformation function. The deformation function in this case acquired this form, 22. And a second mimic constraint, for example, is the density mimic constraint. When the seed density, okay, is equal to the temporal component of the theta sector. In this case, you are solving a first order differential equation in F. Good solution is given by 23, okay? But here you have two mimic constraints, then you have, for example, two solutions, two different models. In the first case, when you are mimicking the pressure, the radial metric potential acquired the force given by 24, as you can see, okay? And in the second case, is a simple one given by 25. As you are mimicking the first case, the pressure, the total pressure becomes 26. And this is quite important. Why? Because the total energy momentum tensor is the perfect fluid energy momentum tensor components plus the theta and mu components. Then in principle, the total radial pressure is the isotropic pressure plus alpha times theta RR. Okay, but as you are mimicking, the pressure is equal to theta RR, then the effective or total pressure is given by 26. And if you do the same, if you compute the total density using the second case, you will obtain 27, okay? But here there are some consequences. Let's see. First of all, as you are modifying the radial metric potential, it means that you are modifying the gravitational mass function. Then you are modifying the compactness parameter, the mass radius ratio, okay, of your system. But I have decided to put this comment because I think it is really important, at least from the theoretical point of view, When you are modifying the mass, because you are introducing, in this case, an anisotropic behavior, the Buch-Dad limit is no longer valid because Buch-Dad limit, okay, the Buch-Dad limit was found using a perfect fluid matter distribution. In this case, when you are introducing a different behavior, in this case, an anisotropic behavior via gravitational decoupling by means of minimal geometric deformation approach, the upper bound of this compactness factor changes, and its upper bound often depends on how you are introducing this anisotropic behavior into the stellar interior, for example, okay? Another thing is the surface redshift also is changing, because as you can see, the surface redshift, as you can see here in 28, the surface redshift depends on the compactness parameter, depends on the mass radius relation. But now your mass depends on alpha. If you are varying alpha, if alpha is taking different value, okay, it means that the mass, the gravitational mass is changing, then a distant observer will detect a more compact distribution in comparison with the isotropic case. We know that, okay, we know that, but those are some of the consequence in applying gravitational decoupling by MGD. Here in this comparative picture, okay, in this comparative picture, you have the starting point is an isotropic seated space-time. It means that alpha is equal to 0. Okay, this is the simple case. And then you have two alternatives. We are here on the red bubbles, okay? On the red ball. You have minimal geometric deformation means F star, okay? G is equal to 0 and F star is not equal to 0. The main consequence from the theoretical point of view, physical, astrophysical consequence, for example, if you are studying compact star, for example, you are changing the mass function and consequently you are changing the gravitational redshift. For example, if you apply the extended MGD case, okay, I'm not going to talk about this one, but just see the difference. The extended MGD case means that now you are deforming both. You are deforming both metric potential. In this case, obviously, you are changing the gravitational redshift, again, the mass function, but also you are changing the observer proper time because you are changing the temporal component associated with this quantity, okay? And finally, just I want to point out some physical consequence about the uses of this Mimi constraint, okay, about the Mimi constraint approach. At the beginning, I told you, okay, we are going to talk about the Mimi constraint approach. We are going to see what the effects are, okay, after minimally deform the space-time. As you can see, there are some consequences independently if you are using the pressure Mimi constraint or the density Mimi constraint, okay? There are some consequences, but the question now is, do those restrictions really introduce modification in the stellar interior? In the case you are studying stellar interior, for example. And the answer is not at all. Not at all. Why? Okay. Okay, why? Let us analyze the pressure-like Mimi constraint, okay? For the density, okay, the situation is almost obvious, but for the pressure, is not at all. When you are employing the Mimi constraint approach for the pressure, okay, in this case, the total pressure should be 1 minus alpha times the original pressure, or the seed pressure, the isotropic pressure. As we know, inside this, in the stellar interior, inside the star, the pressure, the radial pressure should be positively defined everywhere, okay? Everywhere, with its maximum at the center of the star and its minimum at the boundary of the star. Okay, imposing this condition, then we have that the coupling constant alpha should be less than 1. On the other hand, the anisotropic behavior introduced by the theta sector, okay, if you want a more stable configuration, the anisotropic factor should be positively defined. In this way, this extra ingredient is introducing a repulsive gradient counteracting the gravitational gradient, okay? In this way, you can avoid the gravitational collapse. So if you take into account this condition for the pressure-like mimic constraint, then alpha should be positive. It means that alpha is restricted to be between 0 and 1. This is the first consequence, okay? You have a natural upper and lower bound on alpha if you are using the pressure-like mimic constraint. But the problem in using this mimic constraint, is that when you evaluate the decoupler function at the center, this function vanishes. Okay, this is correct because the F function is involved with the deformation of the radial metric potential. And as you know, the radial metric potential is related with the gravitational mass. And we know at the center of the stars, the mass is 0. Then F should be 0 at the center. This is not the problem. The problem is that when you evaluate F at the boundary of the star, the F star obtained from the pressure-like mimic constraint, F is also 0 at the boundary. Then, suppose you want to do an observation. Suppose that you want to compare your toy model. You start, for example, for a perfect fluid, and then you suppose you have a second toy model, and you have introduced the anisotropic behavior using the mimic constraint, the pressure mimic constraint, and then you see, okay, let me compare both objects. Let me see if I can detect if this is a perfect fluid or an anisotropic one. Let me check it. I know we cannot go inside the star and take a sample. We cannot do that, but we can do direct or indirect measurement. For example, we can measure, as you know, the gravitational redshift, and then we can determine, for example, the size of the star or maybe the mass, its composition, etc. But in this case, if you are using this mimic constraint, as the FR function is vanishing at the boundary, it means that this function is not contributing to the mass of the star in this case, because you are measuring the total mass. It means the mass function evaluated at the boundary. But if this function is disappearing at the boundary, then it's not contributing. Then the conclusion in using the pressure-like mimic constraint is that you cannot distinguish between an anisotropic and its anisotropic counterpart if you are using this mimic constraint. Okay, I'm talking from the theoretical point of view. All these stars are from the theoretical point of view. But at least you are solving the problem in a consistent way. But if you go beyond this superficial analysis, you can see that this mimic constraint, for example, is not introducing anything. You cannot differentiate that through, for example, astrophysical components, measuring for example, the gravitational redshift. If I compute the gravitational redshift of my toy model, my perfect fluid toy model, and I have one numerical value, for example, and then after perform gravitational decoupling by MGD, I compute again the numerical value for the gravitational redshift using the pressure-like mimic constraint. I will obtain the same numerical values. Okay. For the density mimic constraint, the situation is more involved. It's different, but I am not going to discuss this here, okay? Because this is just an introduction, as I told you at the very beginning of the talk. But I want to show you the consequence in using at least the pressure-like mimic constraint and how to generate viable solution from the theoretical point of view, from the physical and mathematical point of view, using gravitational decoupling by means of minimal geometric deformation approach. So as conclusion, just I have only one conclusion, despite this pitfall regarding the pressure mimic concept. This methodology is really wonderful methodology. As I told you, it's a very active research field nowadays. So as a conclusion, just I have only one. The big one, the most important one is that gravitational decoupling by means of minimal geometric deformation approach is the first simple, systematic, and direct method to decoupling gravitational source in general relativity and beyond it. Okay, this simple protocol is really a powerful tool to solve many problems, not only at the level of toy model representing compact objects such as neutron star or quark star, also, for example, to obtain hairy black hole solutions or to obtain new wormhole spacetime, despite these latest one are purely theoretical devices. I know that, but you can explore many things in the cosmological concept to modify gravity theories, and this methodology allowed us to obtain in a closed form, in an analytical way, good physical results with very high precision and in the concept of the physical interpretation. So those are some of the references, okay? And thank you very much for your attention.